A beam AB has mass m and length 2a. The beam rests in equilibrium with A on rough horizontal ground and with B against a smooth vertical wall. So there's friction at the ground, but not at the wall. The beam is inclined to the horizontal at an angle of theta as shown in the diagram. The coefficient of friction between the beam and the ground is mu. The beam is modeled as a uniform rod, so the weight acts in the middle, resting in a vertical plane that is perpendicular to the wall. Using the model, show that mu is greater than or equal to a half cot theta. So let's start by drawing a force diagram. So it's uniform, the mass is m, therefore the weight of mg will be in the middle. We have two reaction forces, one at the ground, one at the wall. Let's call the one at the ground Ra and the one at the wall Rb. And then we will have a frictional force as well. The frictional force will act towards the right to stop the ladder from sliding down the wall. Alright, so there's our force diagram. Let's think about what we want to do. So we're trying to show that mu is greater than or equal to a half cot theta. So there's a few equations and an inequality that we can form in this scenario. The inequality that we can form is that friction must be less than or equal to mu r. That's the only way that we can get an inequality in this scenario. But as you can see, that is not the equation that we have here. So we need to involve some other equations too. The three other equations that we can get are a moments one. So we can take moments about any point and then do clockwise equals anticlockwise. Vertical forces sum to zero, so upward forces equal downward forces. Horizontal forces sum to zero, so forces to the right equal forces to the left. So let's form those three equations, or write down those three equations. Let's start with the moments equation. So we need to pick a point to take moments about. The ground is probably the best point, as if we take moments about this point A, the forces of Ra and F as they act through that point don't have a perpendicular distance, and therefore don't have a moment. So taking moments about that point, we need to consider the perpendicular distances from the line of actions of the two forces that will have moments. So this is the line of action of the weight force. The perpendicular distance from that to the pivot will be this distance here. So we know that this length, as it's a uniform rod, would be A. So considering this triangle, the adjacent side over here will therefore be A cos theta. So that there is A cos theta. And then for the perpendicular distance from this force to the pivot, again, here is the line of action of the force. The perpendicular distance from the line of action of the force to the pivot is this distance here. That distance is the same as this distance. We can use the whole triangle. It's a right angle triangle. The hypotenuse is 2a. This distance here will therefore be 2a sine theta. Okay, so now we can do our moments equation. Clockwise moments equal anti-clockwise moments. So let's start with the clockwise moment of the force mg. That would be mg times the perpendicular distance, which is a cos theta. That will equal to the anti-clockwise moment, which would be rb multiplied by 2a sine theta. So that's equation 1. And now we can consider the vertical and horizontal directions. So horizontally, F must be equal to rb. Those are the only two horizontal forces. This towards the right equals this towards the left. So F is equal to rb. That's equation 2. And then in the vertical direction, upward forces equal downward forces. Ra will equal to mg. Let's call that equation 3. And then we also have the one that we discussed before. The frictional force is less than or equal to mu r. In this case, the r would be the reaction force of the ground, so that would be Ra. That is equation 4, or inequality 4. Okay, so we need to combine these four equations and inequalities to make mu is greater than or equal to a half cot theta. So the only variables that we have in this inequality are mu and cot theta. So those are the only two things we want to have in the end. We want to therefore get rid of things like F and Ra and Rb, Mg, etc. So starting with this inequality that we have here, let's try and get rid of F and Ra. We can do so with equations 2 and 3. So putting in equations 2 and 3 into the inequality 4, replace the F with Rb and replace the Ra with Mg. And that then becomes Rb is less than or equal to mu mg. Let's call this equation 5. We don't want RB in there either, so now we can use the first equation, rearrange that for RB, and then sub that into there. So what I'll do first is I'll rearrange that first equation. So the A's cancel out from that equation. If I bring the 2 to the left-hand side, we get a half mg. So let's start with that. So RB is equal to a half mg. Now we'll deal with the trig functions. So we have cos theta over here, sine theta here. Bring the sine to the left. Cos divided by sine is cot. So it'll be a half mg cot theta. So this is still equation 1. Now we can put equation 1 into equation 5, and we end up with a half mg cot theta is less than or equal to mu mg. So I've just replaced the RB with this, so put that into there. The mg's cancel out, and then just rearranging this, mu is greater than or equal to a half cot theta as required. And now on to part B. A horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. This force acts in a direction that is perpendicular to the wall and towards the wall. So basically that means the force of kmg acts at point A directly towards the right. Given that tan theta is equal to 5/4 and mu is equal to a half, and the beam is now in limiting equilibrium, use the model to find the value of k. Alright, so let's draw that force of kmg on our diagram. It acts towards the right at point A. So we can consider forces acting horizontally. We have the F and the kmg, we have the RB over here to work out what this value of k would be. But a problem that we have is that we don't know which way the frictional force acts. It could be towards the left or right, depending on how big kmg is. So you can imagine if kmg is quite large, if this pushing force towards the right is quite large, the ladder may want to slide up the wall, and therefore slide towards the right at point A. The frictional force will therefore act towards the left to try and oppose this. Similarly, if the value of kmg were quite small, there may not be enough force towards the right to stop the ladder from sliding down the wall, and therefore to the left at point A. The frictional force would have to act towards the right to try and oppose that desired motion of sliding. So then how do we proceed? We can work out what these forces of RB and F would be. We know that it's in limiting equilibrium, so if it's in limiting equilibrium, we can work out what F would be. And once we have those two things, we can try to piece together a picture of what's going on here. Alright, so let's start with the frictional force. So the frictional force is equal to mu r. It's the reaction force of the ground, so it'll be Ra. And we know that mu in this case is equal to a half. So the maximum frictional force is a half times Ra. The reaction force Ra is equal to mg. That's what we worked out in part A. That still applies here. The vertical forces haven't changed. So the frictional force is equal to a half mg. Now let's think about the reaction force from the wall, so Rb. If we consider the equations that we derived in part A, this one no longer applies. The frictional force is no longer equal to Rb, because we now have some additional horizontal force of kmg that needs to be included in our equation here, and we also don't know which way the frictional force acts, so we can't use that equation. One equation that doesn't change in this new scenario is equation 1. Equation 1 is exactly the same if the force kmg were there or weren't there. Equation 1 was the moments equation. The reason it's exactly the same is because this force of kmg, because it acts from point A, it has no moment, it has no turning effect about point A. The perpendicular distance to this point from the line of action of that kmg force is 0. So that means the moments about point A would be unchanged. The moments about point A would just be still due to this weight force over here and to this normal reaction force over here. Therefore, this equation is the exact same as before. Equation 1 is the same as what we have over here. Rb is equal to a half mg cot theta. We simplified that earlier in part A. This is now still true in part B. From that, we can work out what Rb is. We know what tan theta is. Tan theta is equal to 5/4. So therefore, cot theta, which is 1 over tan, would be 4/5. So Rb, which is equal to a half mg cot theta, a half mg times cot theta, which is 4/5, would be 2/5 of mg. Okay, so now we have the frictional force, the reaction force of the wall. How are these two things going to help us? Well, let's look at our diagram and write those forces in. So the reaction force of the wall was 2/5 mg. So that's RB. The frictional force is a half mg. So if the frictional force were to act towards the right, if the frictional force is a half mg and it acts towards the right, that force is actually bigger than the 2/5 mg, the 0.4 mg that we have acting towards the left. Therefore, we can't have an additional force of kmg acting towards the right, as the overall force towards the right will be bigger than the overall force towards the left. So therefore, the frictional force has to act towards the left. So let's change the position of that F. That now acts towards the left, and we know its magnitude is a half mg. And now, from this new force diagram, we can consider the horizontal forces and then work out what kmg is. We have 2/5 mg going towards the left, a half mg going towards the left. Both of those two forces towards the left will equal kmg towards the right. So that's a half mg plus 2/5 mg is kmg. The mg's all cancel out, and then k is equal to a half plus 2/5, which is 9/10.